just like the plus of it?
I didn't do that.
I
kept doing that.
Oh, you just kept doing transfer?
Yeah, so then I just put it in
Okay.
the Y's.
Okay.
I think it's in the how it was written in.
Yeah.
I put them in, then got that.
Yeah.
All right, so
Okay.
for the VLSI class,
Sure.
we have the
Done?
AOI logic, which is AND or inverter logic, for to form schematics of by using transistors. This is how we form all the gates. So that's why we cover static logic gates, fundamentals actually, and then from the schematic, we design layouts from it. Even though these are a relatively very traditional way of doing layouts, but it's still very useful. The reason for that is if you are synthesizing a large scale integrated circuit, you definitely use all these EDA tools like Cadence and Synopsys. But for a lot of, it's called mixed signal circuits, which includes analog and digital. And so a lot of gates are actually drawn by hand. There's no way that I can use the gates from the standard cell library. I mean, a lot of terms, but you guys will be able to know what they are down the road. But so it's still very useful because we are forming gates, we're drawing gates, and put the gates into a symbol, and we're using the symbol to draw and design larger scale of schematics, and we convert that schematic into layouts, and then we compare layouts and schematic. It's called LVS, and if it passes LVS and passes DRC, we claim that as a success of the integrated circuit design. That's how that works. But how do we design layouts? I mean, you can, because space in IC design is an important topic. We need to save space. So that is why we need to learn how to do stick diagrams. And so this whole week we are focusing on stick diagrams. Make sure everyone can be really good at that. And there will be 2 quizzes. So Wednesday there will be 1 quiz for actually the materials covered last week, pass gate and inverters, switching point, all these kind of things. And on Friday there will be a quiz for AOI logic and schematics. So the reason I'm putting this quiz on Friday is because I have all the notes and lectures, recorded lectures posted, and I hope you can take the time to study it. Okay, there's no way that I can have a homework assignment on Monday and let it due on Friday so you are ready for the quiz. I couldn't do that. You guys have so many other things to work on. So homework 3 you can see still next Wednesday, right? But the thing is, usually, if the homework assignment is not due Friday, you won't study it. So I'm just letting you know that you need to study it while I'm lecturing. So Monday and Wednesday's lecture, you need to study this lecture video and notes, so you'll be ready for the quiz on Friday. So this quiz on Friday is just giving you a little bit of pressure to let you just study it. If I don't have this quiz on Friday, I can imagine homework 3 is assigned on Monday, and you will start working on it over here. Or maybe Tuesday night, Tuesday midnight. That's where you will start working on it, right? So that won't work really well. So this is a little pressure giver. Make sure you study it. Okay. Now let's get into the topic. First, take a look at the lab. Is that tomorrow? Okay, and this is an inverter. I thought we already did it. Still not did. Okay, so it's going to be this week. All right, this week. Pretty straightforward. I probably will talk about the details Tuesday morning a little bit. It's very interesting. Tuesday will be a swimming day for me. You can imagine it's really it's actually rushing. A lot of times I have to. I'm not walking my dog, but I have to collect the waste of the dog, right, in the morning. And then I have to do breakfast for my kids. And then the kids are gone, I just rush to the rec center and swim for 2K and then come back. That is why last week I was a little bit late, because I just got out from the swimming pool and 15 minutes from rec center to campus. It was exactly 8 a.m. I should be like even 10 minutes earlier so I can get everything set up and be ready for the lab. Anyway, so, but I will talk about the details of the lab on Tuesday a little bit, maybe 10-15 minutes. It's a really simple lab. Okay. Now let's take a look at it. How do we form a NAND gate by using transistors? We all know that PMOSes are good at doing what? Passing ones, right?
Yeah.
And NMOSes are good at passing zeros. So in that case, we form a CMOS, complementary MOS circuits, right? And for NAND gate, and we all know the logic for the NAND gate. It has two inputs and one output, A, B, Y, and this is A and B NAND, right? It's NAND. It's and NOR, right? And not. It's a NAND gate. So the truth table 0 0 0 1 1 0 1 1, and for all zeros, because it's an logic under the bar, so it's going to be 0 all the time, and by inverted the zeros is you are getting a 1 for all of them, right? And the last one is 0. Since we know that PMOSes are good at passing ones, and we are dividing this by 2 sections, and we'll let the PMOS do the job for the ones and let NMOS do the job for the 0. Because this is the output, right? This is the output. So these will use PMOS to pull this out to VDD to give a 1 to the output, and we'll let the NMOS pull it down to ground to give a 0 to the output. So how do we do that? A PMOS is you need a 0. Remember that? Because PMOSes are good at passing ones, so we place the PMOS on the top, directly connect to the to VDD, and we need a 0 to turn it on. Do you agree with that?
Yeah.
Why?
Like 0.
Since you told us.
Oh yeah, because
Why? Why is that? Why is this will turn it on?
that means the gate voltage will be
Yeah, we're looking at the VSG, right? VSG. So what is VSG in this case?
5
It's a VDD, right? It's the 5 volts. 5 volts is a lot larger than the threshold voltage for the PMOS, which is 0.9 volts. Is 1 enough to pass it? No, since we have 2 inputs, so we need the 2 of them, and we would like to put them in parallel. Why is that? So 1 is for A, 1 is for B. Because of the logic. See? 0 0, so which means when both of them are giving a 0, are given a 0, okay? So which means both are on. Both PMOSes are on. If both PMOSes are on, I'm shorting, here's V out. I'm shorting V out to VDD. It doesn't matter which one's on or both are on. You just need one of them is on at least. So VDD will be put up, right? Can go through this pass, or both. Doesn't matter. Make sense? So what about the second one? 0 1. Like I told you, you just need one of them to be on. Same to the third case. If one of them is on, at least one of them is on, I will be able to pull V out to VDD. And this circuit works perfectly for this logic. You see, it's either both on or one of them is on. It will be shorted to VDD. Make sense? So this circuit will cover these 3 sections or entries perfectly.
you need NMOS for the full.
NMOS will pull it down to 0. So PMOS is not dealing with zeros. So NMOS will deal with the 0 over here. So how do we do the NMOS? You'll see the both, with NMOS you need 1 to turn it on, to turn on the gate, right?
You get 2 NMOS.
Yeah, two NMOS has to be on at the same time, right?
Yeah.
Why? Why 1 0 is not 0?
Because then one of the PMOS is on. It's going to go up, right?
Because the truth table, it tells you it has to be both on in order to give a 0. So what kind of circuit should we use? Think about it. For parallel, right? One of them is on, done. You have 2 paths. 2 pathways to go to VDD. Doesn't matter. If this is blocked, we still have the other one. It's just one of them is on. But for the NMOS, has to be both on in order to make that happen. Both have to be on to pull this down to ground. And you need two inputs. So you need two transistors. So basically two NMOSes, two PMOSes. So now already have two PMOSes covers the top 3 entries, and we need another two NMOSes being configured or being connected in a certain way that is able to handle this logic here. How do we want to connect the circuit?
Series.
Two NMOSes in series, great. How do we make the connection to the gate?
I guess one is A plus B.
Yes. Okay, so in that case, this will be the first, this will be the A input, B input, and that's the NAND gate. And here's the output with the bubble here, right? So this circuit will implement the logic in the truth table here, and that's why this is the NAND gate. Okay? Any questions on this? No? What about NOR? So let's start with the logic first. So NOR is giving you this, right? This. A, B, Y equals A or B not. A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. Done. So divide it into sections and let the PMOS combinations to figure out the top entry. So 2 zeros means what? 2 zeros of the gates of the PMOSes means what? They have to be on or off at the same time.
But no, they aren't.
They have to be on at the same time. The PMOSes need a 0 to be on, right? So the two PMOSes has to be on at the same time in order to pull this up to VDD, to 1. So how do you want to connect the PMOSes?
In series?
Two PMOSes in series. What about NMOSes? Look at the options. As long as one of them is on, doesn't matter, both or one of them, doesn't matter, and it is able to pull it down to ground. Okay?
Yeah.
So definitely the NMOSes will be in parallel. Here will be the NOR logic. So here's a conclusion. Always think about either the NAND circuit or the NOR circuit. And if you need it's an AND logic with a bar on the top, then you need a PMOS in parallel on the top and NMOS in series at the bottom. And if you need a OR logic and a bar, you need a PMOS in series on top and NMOS in parallel at the bottom. That's a conclusion. Okay, we can keep using this conclusion for the any type of logic. It doesn't have to be a very simple gate. It could be like A and B or C or something like that. There will be a lot of different combinations of the logic circuits. And you need to find out the schematic and layout of that logic expression. So
You see it with a black
Sorry. So, actually, since we're using NORs and NANDs, I guess we're going to be focusing on making circuits consisting of those components.
say it again, I didn't get that.
Sorry, I guess like future thinking, because we're going to be doing like adders and stuff, right?
Mm-hmm.
So I guess we're going to be making adders and stuff from NANDs and NORs, like not using like just a regular AND or gate.
So there will be two different versions. If you look at the future lab, there's I think the lab 7 or something, and it's talking about high-speed adders. So if you use AOI logic to form an adder, because you know the logic expressions of the S and C carry out.
Yeah.
You can find out that from truth table, right? So if you can either build the adder circuit by using the gates, gate level circuits, because you know the logic expression of the inputs, right? Or you can use the AOI logic that we are going to cover this week, which will reduce the size of the adder a lot. And that's why we are doing this, right? So if you see adders, it's actually a huge difference. You can see that's a gate. If you use the traditional gates to form a full adder, traditional full adder is this big, the layout.
It's huge.
Right? A high-speed full adder from the AOI logic is only this big. And it's also faster. It's not just a smaller, also faster. Okay? So actually, with the cadence and synopsis tools, whenever they are doing synthesis of very large-scale integer circuits, they won't be able to optimize that for you. This only can happen when you manually do it with the OI logic by looking at the logic expression and then simplify everything down to a shorter logic expression and then design this layout manually. The tool cannot do this for you. But however, you won't be able to handle like billions of transistors and you're trying to simplify logic over there. It's impossible and unnecessary. So they directly use the cadence tools to directly synthesize and it won't be optimized. So all these will be gate level logic circuits being formed by cadence. There were like billions, sometimes 100 billion of transistors. It's not optimized. It's just everywhere. But you know, when you are doing mixed signal design, you manually optimize it. Okay. So one thing you might see for some of the examples, if I have two PMOSes placed in parallel like this, and each one is W over L, so by default you should consider, if you are not using the gates as two separate signals, for example, they are shorted to each other. Okay, the gates are shorted to it's basically one transistor. Just let you guys know. How? Do they have the same length? Yes. But after the combination, what's really happening? Okay, now let's draw it. Do you still remember the shape of the transistor? Okay, this is the transistor. What is this? This little black square here? What is the
Via.
via? Which to which via?
The via from this and M1 to the surface.
It's a metal 1 to diffusion via, right? If it's the PMOS, it's going to be metal 1 to P plus via. So what is this guy?
That would be poly.
Poly. Here's the symbol, here's the transistor, and that's source, that's drain, and that's gate. Okay, so this dimension is what?
That's your channel length, right?
That's length, and this is the width. Agree with that? So for this type of circuit, it's equivalent to this. And in cadence, you just directly place it next to each other, and you don't have to let it overlap, but just to directly put this boundary on the top of this boundary, so they are exactly matching. It's exactly next to each other. So if you do this, okay, I'm gonna ask you guys to tell me can I pass LVS? just by looking at this circuit, I got two PMOSes, top shorted, gate shorted. Okay, I got these two PMOSes, gate shorted. Can I pass LVS or NCC? It's just layout versus schematic. Do they match?
No.
Why?
You need to short the drain.
Drain source. How? Using which layer? Metal one.
Yeah.
How?
Through vias.
Just draw a box. Maintain the same width, so it's not overshooting. Looks weird. Just make it nice and do this, right? Just overlap, so you got these shorted to each other. Do they match? Yes. Okay. But by looking at this one, what's the length of this combination?
It's still the same.
Still L. You are not changing the length, right? What about the width?
It's double.
What about this area? Add it or not adding it?
Actually wouldn't, because it's not technically in the physics. Because wouldn't it just be the combined width?
Yeah, just the poly. It's nothing underneath it. There's no diffusion, and there's no channel actually. You can just imagine it's just a connection, shorting these two terminals to the same. You can imagine it's just the same piece of metal, right? So basically, the width is only 2W, right? So this thing is equivalent to a bigger transistor, one single one, right? It's gonna do the same. It's gonna run the same amount of current if you give a same VSG. It's not giving you a different current going through the channel. They're equivalent, just like you guys know. Similar effect can be seen for two PMOSes in series, like this. If you place these two together, why is there multiple vias? Why is there multiple vias? Oh, yeah, the area is bigger, so it's directly adding backup vias to it, right? To increase what? To improve what?
The time delay?
No. To improve what? Oh, yeah, sometimes, yes, a little bit, yeah. You're right, partially, yes. But also what?
Reliability?
Yes, increase the yield, right? Improve the yield.
Yeah.
So you have backup vias. If one of the vias is failing, you still have multiple other vias making the connection, right? So it's improving yield. And yield is a big deal. How?
You have to connect the poly.
Do you need to connect a poly?
Actually, no, because they're not actually shorted.
Mhm.
It would just be the source. Or the drain to the source. So it would just be a single metal connection through the vias on the two inside.
Mm-hmm. Metal what? Yeah, just metal one. Grab a piece of metal one to make the connection. Can you simplify this? Just taking too much space. And we're trying to optimize it. Are you changing the width? Is the width being changed? No. What about the length? What about here?
That's just metal.
It's just metal, right? I mean, ideally, it just considers the vias are metals, and it's metal one. It's just one voltage node. So the one voltage node doesn't matter how long it is. We consider it's ideal. It's just one piece. If it's just one piece, can we simplify it? Anyway, so here's one L, right? One L, another L. So the effective L becomes 2L, right? No doubt on that. but can we simplify this circuit, this layout? It's just one node. Why do we need a two metal one vias, right? Can we simplify into one? Yes. What about this?
Just have them share the same.
Yeah, share the same. Exactly. Do this. And since it's sharing the same, oh, Jones is too big. Am I changing the length from here?
No.
No, because this is the channel length. This is channel length, still 2L. And also, I'm not changing the width as well. But is this the best version or not? Why do we need a vias in the middle? Why is that?
Because they're still two separate equations.
But I mean, here, do we need any wires or connections in the middle?
Maybe.
I mean, for this circuit, no, actually.
Oh.
We were not connecting to the middle at all. So, which is this metal connection, or this voltage node is not being used. Do we still need these vias and metal one in the middle? So basically, looks like we only need two lengths, right? Two channel lengths. Is there anything else we can do?
I guess technically you could do metal on the beams to like have a better connection.
If we don't really use metal vias or metal wires in the middle, we don't really need this at all. Then what's going to happen if you think about the cross-sectional view here? If you don't even put anything in the middle, what's happening? So if you don't put anything in the middle, there's no vias, no metal. So what else is left?
It's just that. Well.
There's not a well there. I mean, would it just be the P substrate there?
Yeah. So the poly defines the channel length, right?
Yeah.
If there's no poly, there's no channel. You agree with that?
Yeah. So.
Oh, would it just be Fox?
It should be just Fox.
Oh.
Hmm. So the conclusion is you don't really need this in the middle. You can just directly put two sticks over here. And a lot of times these polys are called fingers. It's really interesting because it looks like fingers, right? So this is a two finger. Oh, make you think about raising canes. Oh, you all have really all came from big cities.
I need it. Because you don't remind us of canes. I miss canes.
Uh-huh.
Cane combo.
So you order fingers from raising canes, right? So fingers, these are fingers. But not chicken fingers, they're knife fingers. So these are called fingers. I see this in cadence, actually. You are adding how many fingers to it. The multi-finger configuration, thing like that. So this one has this. It seems like it's all covered by green. But there's no poly, so the cross-sectional view will look like what? Oh, I haven't thought about this, but no, let's think about it together. So, seems like the whole thing, the diffusion. Okay, you got a P plus, this is P plus,
Yeah.
right? P plus and P plus, you got two poly here and one here.
Yeah.
So for this guy, you got a P plus in the middle. I think you still have P plus in the middle, but just no V and metal one.
Yeah, that makes sense.
So just ignoring this P plus, it's just treating this guy as a ideal metal piece or something, right? So you got one L here, another L here. The reason for that is when the whole thing is green, it's a p act. So open that Fox, there's no Fox anymore, I think. Okay? And then the p act is depositing the p plus material into everywhere. And then there's no poly to block it from getting into the wafer, so that's why you are getting p plus here as well. And this is forming two L's. These are the two channel lengths being counted. So eventually, it's effectively it's 2L.
And that's in a in-well?
Yes, it has to be in the well. Yes.
With and there's the in-tap.
We don't have untap.
Oh, in-tap.
There's no untap based on this version. There's no untap yet. But you know, if we have this, if I draw this, right, then you need to draw untap because that's the body contact and short to VD. But for this one, that's a very good question. So how do we draw the untap here for this one? So each one has an untap. Let's assume that each one has an untap, right? It could be N plus here and N plus here, right? So they are just, if you look at the connections, they are just shorted together and shorted to VD. So they are just shorted together and then to VD, right? That's it. Right? Any questions on this? No questions? So AOI means and or inverter circuit. And or inverter circuit. It's not an or inverter, it's and or inverter, right? Three different types of logic. So the reason for that is if you look at the NAND and NOR examples, these are the fundamentals of all these AOI logic circuits. It's basically it's inverting it one more time. You know what I mean?
Yeah.
So if you form a circuit like this, the result will be something and bar on the top. We know where this came from, right? But now we just don't keep asking ourselves why it's like this, has a logic and a bar on top. Let's just don't ask ourselves this question anymore in the future. Is that okay? Are we comfortable with that? Since we already derived everything, we know this works, right?
Yeah.
We know this works, and conclusion is for a circuit like this, eventually this output will have a little logic here with a bar on the top, and then if we are given with a logic in this format, we'll just directly convert into a AOI logic circuit like this. You know what I mean? But don't ask ourselves why. Because it's already demonstrated. Comfortable with that? Okay. So now let's look at more examples. If I have A or B or C, this is pretty simple. How this works. Always think about the NAND and NOR schematic. Okay? Whenever you have OR logic so for the future, if you have a logic expression, what you want to do the first step is you convert everything to one logic expression and have a universal bar on the top. And then you convert it back. Then you look at that logic and find out the schematic. Because a lot of times, how the real world works, you are given with a logic expression, right? Or that logic expression is came from the truth table, and the truth table came from the real world problem. That makes sense. So you are trying to figure out the problem, and then you think about the logic, and then you eventually you get a truth table, because this is what inputs and outputs, right? And from the truth table you do the simplification and the key map and whatever. Eventually you get a logic expression. Okay, the logic expression can look like all different forms, different formats, and from that we convert it into something with a bar on the top. Okay, that's the goal. We convert it to something with a bar on the top, so we know that we can start thinking about the schematic using transistors and eventually form that circuit to implement that logic. Because you can see, no matter what, it's AND logic with a bar. OR logic is OR logic with a bar. Because every time this is being inverted with a certain logic. So look at this one. Similar to what? The NOR gate. The only thing difference is you have one more input. So remember, for OR logic at the bottom of the bar with a universal bar on the top, OR logic with a bar on top, you need what? So for the OR logic, you need a series PMOS on the top, and you need a parallel NMOS at the bottom. Are you getting that?
So, yeah, we just have one more of each.
Yeah, one more each. Why? Always think about these two examples. For OR logic, underneath the bar, we need two PMOSes in series and two NMOSes in parallel. For AND logic, underneath the bar, we need two PMOSes in parallel and two NMOSes in series. OR logic, underneath the bar, we need three PMOSes in series. And we need three NMOSes in parallel. Okay, done. Does it matter which is which connect to which? It doesn't. So here's the output, and this output will be this. That's a three input NOR gate. Any questions on this? Doesn't matter if can I connect this one to the second one here. It doesn't matter. This one to here doesn't matter. I just following the certain order here. First one to the first one, second one to the second one, third one to the third one. But it doesn't matter which one connect to where. It doesn't matter at all. Okay? I'll give you another example. Here's the logic expression from any real world problems, and from the truth table someone find out this logic expression as a conclusion, and we need to design a logic circuit using transistors. Do we have a bar? Do we have a universal bar on top? No. So we need to add a bar on top. But adding a bar is going to change the logic, right?
Yeah.
What you can do, add two bars. Can we? Yes, add two bars. Invert it twice. Bar. Remember De Morgan's law?
I forgot it.
I remember.
De Morgan's law is very simple. It's split the bar, change the sign, right? That's De Morgan's law. Split the bar and change the sign. That's De Morgan's law. How do we do that? A and B. How do we split the bar and change the sign? Okay? Make sense?
So that would be A naught.
Split the bar and change the sign. Split bar and change the sign. That's De Morgan's law. That's it. Okay? And this is given. Now look at this. I added 2 bars. I'm gonna try to get rid of the second bar at the bottom. And apply De Morgan's law. Is this bar on the top of this guy. I wanna split the bar and change the sign. So keep the top bar and split the bar, change the sign. Questions? Bar is A. Split the bar, change the sign one more time. Questions?
We'd have to.
Hmm?
So why didn't you split the sign for the A, or sorry, change the sign for the A, or is it because the 2 bars canceled out, and that's why you got it?
Yeah,
Okay.
yeah. Invert twice, right? 2 inverters.
Oh, okay.
Come back. Any other questions? We're ready. See, we have 3 signal lines, and we have a bar on top. We can start designing the circuit. Okay? Now let's do it. So that's the OR logic. So for OR logic, we need what? OR logic underneath the bar, we need a series PMOSes, right?
Yeah.
Series PMOSes and parallel NMOSes. And the whole thing here is being treated as one entity, and this guy. So for analogic underneath the bar, we need the parallel PMOSes and series NMOSes.
Yeah. Yes.
Okay? Let's do it. So series PMOSes for these 2 signal lines, PMOSes. And the whole thing as one entity, it's doing analogic with this guy underneath the bar. So these 2 things need to be in parallel, right?
Yeah.
So this thing need to be in parallel with that A. So this is B naught, this is C naught, and that's VDD. Any questions on this by far? Always think about the NOR and NAND gate circuits. The NOR gate is like a super narrow head and big legs, right? Big legs. But NAND gate is huge head and chicken legs. Why is always chicken? We need some chicken today for lunch. Does this make sense by looking at this guy and think about the NOR and NAND gates?
It still need the NMOS, right?
I was in the NMOS, I mean, but for now, for the PMOS logic, for the PMOS pulling up to VD, right? So what about the bottom? The bottom we need, so this, for NMOSes, remember the NOR gate? The NOR gate has a big legs, right? So which is parallel to parallel and then in series with this guy. So we can do this, A, and then parallel transistors, B naught, C naught. So my question for you guys is, does it matter if I put the 2 parallel transistors on the top of the N as a one single one, or just keep it this format? So this format, or I, switch it. Is it changing the result? It's not changing the result actually. It's not. You can see this and this, or this and this. It doesn't matter. So A and this and A doesn't matter. So it's the same. So you can put this on the top or this on the bottom. But the only thing is changing is a layout format, which is being covered on Wednesday. So when you do the layout, it has to follow a certain order in order to pass LVS. That's critical when you think about the layout. But now it's not. It's just the logic, get the logic done. Any questions on this before moving forward? No? Page 4. Let's look at more examples. BC. Like this. So apparently we should apply the same method. Directly throw 2 bars on top. So we can combine these two items first. So it can be B not or D and C. That's OR logic. Okay. And moving forward, this could become a top bar, keep the top bar on the top, and then we do split bar change the sign. It's gonna be A naught and B naught or D and C bar. And do that one more time. Wait, this, oh, we changed it, yep, we changed it here. And this becomes this. Right? And this is this. I'll let you go to get your chickens after this, I promise you. Okay. We cannot simplify this further. Let's just directly work on this expression. Start with this guy. It's going to be 2 parallel PMOSes. Parallel PMOSes and in series with this guy. And the whole thing in parallel with this guy. Is that right? Yes. Okay, PMOS is done. Then the NMOS part. So this will be in series and then in parallel. So it's basically in series and in parallel with this guy. And in series with this guy. And that's it. So the output here in the middle is going to be this. Okay, we'll cover more examples on Wednesday. And the quiz on Wednesday is not from this because it's still kind of new. So a quiz on this will be on Friday. And the quiz on Wednesday will be something covered last week. The switching point, the pass gate, NMOS, PMOS, all these kind of things. Okay. Question on this before I let you go? No? Alright, we'll see you guys tomorrow for the lab, right?
Yeah, right here.